Section 2.3, applications of radian measure. First thing we're going to talk about is arc length and area of sectors. So our first formula here is arc length. We use S. I'm not sure where that comes from traditionally, but we're going to say S is the length of an arc. You can see this little blue piece right here. Length of an arc is equal to the radius, so the distance from the middle of the circle to the outside of the circle, times the angle. So the angle is theta. Inside of this angle that the arc, we say subtends, okay, fancy word. But the angle has to be in radians. So if it's not in radians, we have to change it to degrees. Okay, so let's do this problem. Find the length of an arc on a circle of radius 10 units that subtends a central angle of 215 degrees. I like pictures. I didn't draw a picture on this previously, so if we want, we could sketch a little picture to help us understand what's happening. Now, drawing our angles in standard position doesn't matter at all for this stuff, right? So if we have a circle, whoo, didn't mean to move that. Relock it. Okay. So if I have a little circle, grab a little circle drawer. There we go. And I'm going to pick a place for my radius, or like my starting point. So 215 degrees, that would be past 180, right? 180 would kind of be straight across here. So 215 is that, so 215 minus 180, would that be like 35 degrees past 180? So I'm just approximating. The picture doesn't matter at all. They didn't ask us to draw a picture. I'm just making sure we see what we're doing. So we're trying to find the length. It's a really thick highlighter, but okay. We're trying to find the length of that arc right there. But we need our angle to be in radians. So to change our angle in degrees to radians, so we do 215 degrees times pi over 180. Simplify that to radians. In this case, all I did was multiply those together, and so here's my approximate answer to do 2 decimal places. But just in case we need to leave our answer exact, let's double check that. You might have already found it. Ooh, I don't know what that reduces to. This calculator doesn't do fractions for me. I think it does. I'm just not in the habit of using that function on calculators. So it looks like it reduces to 215 over 18. So the 10 and the 180 reduce. And then there's the pi. So if we do leave this exact 215 pi over 18, which is approximately equal to 37.52457.892, and I just rounded it to a couple of decimal places. They didn't tell me what to round it to, so I chose to do 2 places. Please pay attention to your actual assignment and how many decimal places it asks you for. And then, of course, if it were in centimeters, we would have given our answer in centimeters. If it had been miles, we would have been given our answer in miles. In this case, it just said units, so our answer is in units. Example 2, assume the orbit of Mercury around the Sun is a perfect circle. We know it's not. We know it's elliptical if you've studied any of that astronomy stuff at all. But that's okay. For this problem, we're just going to make an assumption. Mercury is approximately 36 million miles from the Sun. So if you imagine you've got the Sun, you've got Mercury out here in a circular orbit around the Sun. So that right there could be called the radius, right? From the Sun to Mercury. So that's 36 million miles. All right, in one Earth day, Mercury completes 0.0114 of its total revolution. How many miles does it travel in one Earth day, right? Because Mercury days would be different than Earth days. So we've got to convert, yeah, we're finding the arc length, correct? So arc length is S equals R times theta. We know R is 36 million miles, but we don't know theta. Theta was given in revolutions. So we need to change theta from revolutions to radians. So we have 0.0114 revolutions And we're going to change that to radians. How do we do that? Do you remember? One revolution means one time around a circle. So what is that in radians? 2 pi. Yep. So that would be 2 times 0, 1, 1, 4. So if we want to leave it in terms of pi, that would be 0.0228 pi, which is approximately equal to, whatever. Okay, so to do my actual formula, find the arc length, how far it travels in one day, I need the radius, which is 36 million miles from the sun. I could write it out in million, like write out all the zeros to make it millions, or I could just say this is in millions of miles. What would you rather I did? Do you want me to write out all the zeros? Okay. So million, capital M for million? Yeah. Okay, cool. I'm good with that. Sounds good. And then we're taking our 0.0114 revolutions times 2 pi, right? Which is 0.0228 pi. Just go ahead and multiply that all together. See what we get. So times 36 times pi. So this says 2.57861925. So we'll say 2.58 million miles in one day. Okay. Any questions about that? I feel like we already found the answer to part 2, didn't we? I think we already found the answer to part 2 in doing part 1. Oh, okay. Maybe not, because that was... Well, I think so. So for question 2, if we're going to find the radian measure for Mercury's movement in one day, that was just the 0.0114 revolutions times 2 pi. So the 0.0028 pi, when I multiply that out, I get 0.0716283125, so I rounded it to 0.072, okay? So that's not hard. We had to use that to do this problem. However, what this problem is asking us for is it's asking us to work backwards. We're assuming we don't know this, and we're going to actually find the answer by using the formula we just learned. So we know that S equals R times theta. And to find theta, the number of radians in one day, we could take S and divide R, correct? So S, the arc length we just found, was 2.58, and the radius from the sun was 36 million. And if we divide that, what do we get? It should be the same answer we got here. So if you want to check and see, which is what I was doing when I was a little bit bewildered on why I had something written down than just this to answer the question. So the whole point of this second question, it's kind of not needed in this exact situation because finding those radians this way was easy. But what if you didn't have this information in part 1? What if all you had was the 36 million miles from the sun and the arc length? Then you could go backwards to use the formula to find the radians, right? That's what this example is saying.